Welcome everyone. Are you ready to learn how to smash the W-shaped problem? I am thrilled to have you here today. Let's unlock the secret to overcoming the W-shaped problem. By the end of this lecture, you will be able to solve problems related to W-shaped structural steel by finding the maximum tensile stress and maximum normal strain. In last lecture, we had discussed about the different shape of structural steel. Now in this we will be solving problem related to the shape of structural steel. The first was the W-shaped structural steel. The problem is given that a 20 feet long W-shape 𝙸𝙽𝙰𝚂 is suspended from one end. From this data you will know the shape of structural steel and the weight in pound per foot of length, and the length of the W shape of structural steel, and also here the modulus of elasticity, also called Young's modulus, which is 29,000 ksi, is given. So in this we will determining the maximum tensile stress and maximum normal strain. So this will be the topic today. We will finding the maximum tensile stress and maximum normal strain. So in this you learn that what is the designation of the W shape, which is the nominal depth is 8 inches and weight in pound per foot of length is 67. So we had this value 67. So if we multiply this 67 to the total length, we will get the value of weight of a shape of structural steel which is 20 feet long. In next slide we will doing this calculation. By finding this, we will get the value of force or load, then dividing by area we will get the maximum tensile stress. So this is the solution of part 1, in which we will finding the maximum tensile stress. So from the designation given in the question, that was the W867, the weight in pound per foot of length is 67. So here I mentioned this, and if we multiply this weight by 20, so we will get the value for 20 feet long W-shaped structural steel, that is the 3040 pound. So now finding the area, because the stress formula is this, that load per unit area. So if we divide load by area we will get stress. So now we are finding the area. For area calculation we are using the steel manual. So each shape of structural steel, for each shape of structural steel we had different section properties are given in the steel manual. So in W shape we are going to the chapter W shape, and then here this designation is given in a question. So in front of this designation we had the area, depth, web, flanges, thicknesses, etc. So here the in steel manual this W867 designation is here. In front of this we had area, that area is 19.7. so we can find the area directly from the steel manual without any calculation. Remember this. So now for tensile stress we know the formula, that tensile stress is equal to weight or load divided by area. We had the value of weight or load, that is the 3040 pound, and divided by area, which is 19.7. By dividing this we will get the value for the tensile stress, which is 68.02 psi. Now we are solving the solution for the second part by finding the normal strain, maximum normal strain. As from the Hooke law we know the formula for the normal strain, that was the maximum tensile stress divided by modulus of elasticity. As Hooke law says that the stress and strain are directly proportional to the up to certain limit. So stress and strain are directly proportional. So stress is directly proportional to strain. So the stress will be equal to modulus of elasticity times strain. So we are finding this strain. So the modulus of elasticity comes to this side, it will be in divide. So the new formula will be that the tensile stress divided by the modulus of elasticity. In question we know the modulus of elasticity, which is 29,000 KSI. So by keeping the same unit, so I'm changing this KSI into PSI by multiplying into 100. It will convert from KSI to PSI. So the new value of modulus of elasticity will be 29,000 into 1000 PSI. So in last slide we had found the value of tensile stress, maximum tensile stress, which is 68.02 psi. So we know the formula for the normal strain, that is the tensile stress divided by modulus of elasticity. In last slide we had found this value, in question we had this value. So by dividing both the value for the tensile stress and modulus of elasticity respectively, we will get the value for the normal strain, which is 2.35 multiplied 10 raised to the power minus 6. This is the solution for the part 2. So we solve the value for the maximum tensile stress and maximum normal strain. So this is the today lecture. I hope you understand it.